Hello and welcome back to Differential Equations, section 3.5 on homogeneous equations and undetermined coefficients and variation of parameters. It is not in the title, but variation of parameters is explained and outlined at the end of the section. So let me just see, that would be all the way back on page 194, literally last page of our lecture. So in the book, so we are going to have all of that in this one lecture, but I'm going to the title, the second part of this variation of parameters. So I'll say 3.5 part 2 and then variation of parameters, so you know that we are covering that method as well. Now, what are these methods for, and why do we need them? Well, last time we talked about constant coefficients, and we also had mechanical vibrations and so on. Now we are going to have those systems, the differential equation, but that differential equation now is going to equal to some driving function, which we would call forcing function, and that function is going to be the f of t or f of x or whatever, right, on the right hand side. So the equation that we are looking at today is an y to the nth derivative, right? So nth derivative of y plus an minus 1 y n minus 1 plus an minus 2 y n minus 2 derivative plus dot 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 plus a1 y prime plus a0 y equals f of t. There it is. So that is our forcing term, and that's the one that supplies extra energy to the system on the left. Now, for our purposes, most of our problems were the second order differential equation, something of the form ax. Let's not use a. Let's use c1 x double. You know what? How about we just use the mechanical one? Why not? Mx double prime plus cx prime plus kx equals, and now we're going to have f of t. So now we are allowing for this. Now I'm going to say that this is 3.7 actually. Sorry, 3.6, this equation. But you understand now that this used to be a 0 in 3.4. And now we're going to learn the method that can solve this equation if that is a function of some kind. Now, this f of t could be polynomial, could be trig, could be exponential function, and we are going to have the setups that you memorize or combinations, combos, there we go. And we are going to have the the list of setups that you use to solve the problem. Now, I love the way they worded something in a book. I always laugh when I read it because they say, let me just find it again. So when given function f of x, or our f of t, is sufficiently simple, we can make an intelligent guess to the general form, right? So intelligent guess, I love it. I call that cases, right? They call it an intelligent guess, but you just need to know, right, what form to use as you're setting up. And I will actually show you the method how you can obtain that rather than memorizing them. And then you pick your poison. Do you want to memorize it, or you want to just learn one method which tells you all of these, because you're bound to run into something that is not on the list, and then you're doomed, right? You have to use the method anyway. So let's take a look at an example of this. Oh, first, sorry. So the solution now is going to be given by y is equal to yc plus yp. And we have to now get the terminology straight, because this p is going to stand for particular, but it's not going to be the particular solution like last time so far. It's going to mean something different, which is terrible, but such is life. Deal with it. So our solution y for our differential equation over here will have the complementary solution. Let me just box this first. Complementary solution, let's point the arrow into complementary solution, and I'll say due to homogeneous part, and then this one is due to forcing term, and this is where we use undetermined coefficients or variation of parameters. So we have the complementary solution. Guys, this part is what you have learned so far. It stays unchanged. The only thing that we are learning today is to come up with this extra piece that it's added as a term to your solution, and that one is going to be computed through undetermined coefficients. So now our total solution will contain what we say complementary solution due to homogeneous part and particular solution due to forcing term. And that's where you use undetermined coefficients. Now let's go and take a look at the simplest case possible. Kid on a swing, right? And you have oscillation because the kid goes left and right and left and right, right? If you look at the sideways, at the swing sideways, and that could be perceived as a wave because the kid oscillates as the time goes on. So we have the oscillation motion as the time goes on. That's a wave. Kid goes back and forth, but there is someone standing on one side of the swing constantly pushing the kid with, certain frequency, certain force, which would be the amplitude. And since that's done periodically, we are going to pick a cosine input for the forcing term. So let's just have the most basic function you can think of. So let's go with x double prime plus, let's go with, 64x equals, and on this other side, I'm going to have a forcing term of cosine, let's say 3t. So the amplitude of this cosine is 1. So that's going to be 1 unit of force that you push the kid with. And this is how frequently, right, you push the kid every time the swing comes back. You push it with the same force. So this system would go on forever, right, in this way. And we want to know the equation of that governs this motion, because over here we have the kid on a swing, and over here we have the person that it's pushing, and that system works together. Now, the problems today are very similar to the problems you had before. Your job is to solve this first, and you will deal with that as x double prime plus 64x is equal to is equal to 0. So that's your life. And you know how to solve this, right? You have your r squared. This is on your exam coming up because this is in 3.1 and 3.3 and 3.4. They all have this. So this is definitely a problem that is on the exam right here. This is the new stuff that it's not on the test, but this stuff is there. So we have r squared plus 64 equals 0. R equals plus minus 8i, which gives you the solution of y complementary, because we are only dealing with this part, which we say homogeneous, right? Homogeneous or homogeneous, whichever way you want to pronounce it, when it's equal to 0. And that's going to be your C1 cosine 8t plus C2 sine 8t. Nothing is changed. Absolutely nothing is changed. You have your solution here. Now, here comes the new part. So what now we want to do now is to find the form, or you memorized it. We want to find the form for undetermined coefficients for cosine 3t. So if you are assuming, remember the intelligent guess, right? If you're assuming your yp to be cosine 3t, you differentiate to get negative 3 sine 3t, and you differentiate again, and you get negative 9 cosine 3t. All of these together, put together into the form of the solution, look like a sine 3t plus b cosine 3t, and that's what we're going to call yp as our test, and we just need to determine coefficients. So you take what you have here, exponential function, polynomial function, trigonometric function, combination of any of those functions. Control C, Control V, and take this many derivatives. If this is a third degree problem, you take 3 derivatives. So once you come up with all possible derivatives, the way to put all of them in one bag is to say, well, they all have sines, they all have cosines, and they all have different numbers in front. You see, this cosine 3t has coefficient of 1, and this cosine 3t has a coefficient of negative 9. So instead of me writing 1 or negative 9, I'm going to put b, any coefficient. Now, we only have one sine with a negative 3, but if this was a sine problem, you would have 2 sines in a derivative and 1 cosine, in which case it kind of should be common sense that you should use a and b, right? And those are your undetermined coefficients, hence the title of the problem. So what I need to do now is to determine those coefficients. And determining these coefficients is going to be very simple. Take derivative first and second of this and plug them all in here. Obviously, second derivative and the third derivative. And I just noticed that I'm doing wrong notation because these are x's. So I should have x's everywhere, because my dependent variable is x and the independent is t. So they should all be x's over here. All right, so now that I have the form, now as I said, what I wrote in blue here is the procedure, how to come up with this. Some students are going to memorize this red line and just continue from there without doing any of this process of figuring out what this should be. So when you see a trig function here, whether it's a sine or a cosine, this is your immediate response. You do not have to have this if you memorize the form. And that is listed in a book somewhere, in a chart, on page 191. So page 191 lists the cases if you want to memorize them. I hate memorizing, so I never did. I go through the blue procedure to come up with what xp should look like. And then the particular p prime is going to be 3a cosine 3t minus 3b sine 3t. And xp double prime is going to be negative 9a sine 3t minus 9b cosine 3t. So now we use this one and this one, plug into ODE. So we have x double prime plus 64x equals cosine 3t. So x double prime is negative 9a sine 3t minus 9b cosine 3t plus 64 of x, that's the vanilla one, a sine 3t plus b cosine 3t, all of that equal to cosine 3t. There it is. This calculation here should immediately remind you of your partial fraction decomposition. If you remember, when you had that one long line, you write two equations, you solve the system, you have your coefficients. So now we pile up all sines and all cosines and equal them to the coefficients of the right-hand side. So on the left, I have this as the a sine, and here is my a sine. So that's 64 minus 9. Well, that's 55a. So 55a sine 3t. And then I have minus 55b cosine 3t is equal to cosine 3t. And now you equal the coefficients on the left and the coefficients on the right. Do I have a sine term on the left? Sorry, on the right? No. So 55a is equal to 0. No sine 3t on the right. And then 55a equals, negative 55b equals 1, because cosine 3t is 1 times cosine 3t on the right. You're just comparing the coefficient. See, if you look at this two, I will say this is out because there's no sine on the other side, so that's out. But if you compare the two cosines, when the cosines cancel, you just have your negative 55b equals 1. This is the same idea, guys, you used in partial fraction decomposition in Calc 2. This should not be weird in any way. So we calculated that a is 0 and b is negative 1 over 55. So my xp is, my xp is this. And I just figured out that a is 0 and b is negative 1 over 55 cosine 3t. So I can write the solution. Solution x is equal to yc, xc in this case, was c1 cosine 8t plus c2 sine 8t and plus xp, which is minus 1 over 55 cosine 3t. That's the answer. Welcome to Undetermined Coefficients, which by the end of the problem you are supposed to determine, right? And then plug them into the equation. Why did I do the trig problem first, where we could have done this with polynomials and have it easier? Because polynomials don't really have the application. I started this problem as telling you that the kid was swinging left and right on the swing, right? With the angular velocity and blah, 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 all of the stuff that you can observe if you watch the kid, right? You're looking at the seesaw sideways. So the kid is, right, this is where the thing, so the kid is sitting here. And then the kid goes like that. There is another person standing over here. Every time the kid reaches this side, the person pushes. This person is that, the kid swinging left and right is this equation. It is very easy to connect this to the world around you, because that's what this is all about, differential equations. Model the world around you all the time. So the equation on the left is the kid on a swing, let's say. The equation on the right, the cosine 3t, is you pushing the kid. We solve the left part the same way we learned before, nothing new there. And then we just plow through calculations for this. All right, let's take another example. It will always be the same, right, the way you calculate these things. I want to go into the homework, pick up something else. So let's now pick, there is a equation with hyperbolic sign on the homework. Yeah, why not? So let's see, y double prime, this is problem number 2. Y double prime minus y prime minus 2y equals to 3x plus 4. Now note that we don't have t now, it's x and a y. So x is our independent variable. I have to solve y double prime minus y prime minus 2y equal to 0. This is your standard good old r squared characteristic equation. Minus r minus 2 equals to 0. And then you have your factoring here, r minus 2, r plus 1. And you're getting your distinct r's, 2 and negative 1. Your yc solution is c1 e to the 2x. Remember, x is now independent, not t. Just gotta be careful about these things. Plus c2 e to the negative x. And now we need yp over here. Now, what is the form of yp? Well, if you are to take a couple of the derivatives here, right? You have your 3x plus 4. That's your function. Take the derivative of that, you get 3. Take another derivative of that, you get 0. You immediately see that the form for your answer here, so for your setup, is that yp should be of the form ax plus b. Again, this is a 3 over here. So why can't we just immediately have a 3 for a? Well, you can't really, because if your problem was x squared plus 3x plus 4, then the first derivative is 2x plus 3, the second derivative is 2, the third derivative is 0. So now you see that the x term changed its coefficient, right? So the x changed its coefficient if this was a different function. You are not learning this example by example. You should learn the concept for, like, the procedure for the entire set of these things, and then you can, right, live. So we are going to have ax plus b, because those are all possibilities you have. You can see over here that the constant was 4. Well, b is equal to 4, b is equal to 3, b is equal to 0, right? So when you have a constant term, it keeps changing its value. And then the linear term should also be changing the value if we had a higher order derivatives. I mean, higher order polynomial to have derivatives change its point. Okay, so what are we going to do now for this problem? Let's go and take a look at the derivatives, right? So we have yp prime is going to be a, and yp double prime is just 0, which is okay. We plug those where they belong in their differential equation. So differential equation is y double prime minus y minus 2y equal to 3x plus 4. And
minus y prime, right?
Minus y prime. Excellent. I was just testing everyone, and you won. Okay, great. So now yp gets there, y prime gets there, y double prime gets there. So 0 minus a minus 2 times ax plus b needs to be equal to the 3x plus 4. You have your a and b undetermined coefficients, and we can use this equation to determine them. So negative a minus 2ax minus 2b, or not 2b, is equal to 3x plus 4. I have negative 2ax equal to 3x. X and x, right, coefficients, we don't put them there. So a is negative 3/2. I have my negative a, maybe I should put a line through. I have my negative a minus 2b equals to 4, because these are the ones that have no x, and that needs to be compared to the one with no x on the other side. So minus a minus 2b equals 4. But we already know that a is negative 3/2, so plug that in there. We have 3, we have 3/2, go away, 3/2, right? Negative and negative make a positive. So we just have a 3/2 minus 2b equals to 4, which gives us negative b is equal to 5/2 when you subtract 3/2 from, right? That's 8/2. So 8 minus 3 is 5. And then we divide both sides by negative 2. So b turns out to be negative 5/4, right? Because when you divide 5/2 by 2, you get quarters. So 5/4. And there are the coefficients. So now the solution is C1 e to the negative 2x, no, to the 2x, plus c2e to the negative x, minus 3/2 x, minus 5/4. Now, notice that this is a second order differential equation, and you still have two constants there, c1 and c2, which you can compute if the initial conditions are given to you. That's another calculation on top of all of this to figure out c1 and c2. This is just a general solution that you guys obtain by this method. Right? It's a ton of fun. These, which are labeled simple problems, are simple problems because repetition doesn't come up. The evil problems are the ones where you have a repetition between the complementary solution and the YP solution. Right? So, with that being said, let's open the gates of hell. What happens when you have a repeated solution? You have to multiply those e's by t, for instance. You have to multiply by those x's with ln x, which now is going to start involving product rules and make these calculations far longer than what we would like. Now, I want to obviously start this chapter of problems with something that should be very, very, very simple. So let's say you have the same problem as we had before of y double prime minus y prime minus 2y equals, and over here I'm just going to say 4e to the minus x. So there are only two cases that I can pick here that would make our life miserable, and those are obviously e to the 2x or e to the minus x, because those are the solutions that are on this side. And when we create that repeated solution, we have to use the method we learned back in 3.1, right? Where you have to pre-multiply it with that t, or in this case x, independent variable, to create the independent solution, right? Because the Wronskian would not work out in that case. So this portion here does not change. Your y complementary is still c1 e to the 2x plus c2 e to the negative x, right? That's still good. Now, the hell breaks loose on the other end, where we do our undetermined coefficients. When you say that your f is 4e to the minus x, and then you take a couple of these derivatives, it becomes minus 4e to the minus x, then plus 4e to the minus x, and you say, oh, it's ae to the minus x, right? Because the coefficient in front keeps changing between 4 and minus 4. So you are claiming that the yp should be e to the negative x. But no, it's a repetition. And because it's a repetition, we have to bump it by x. So I'm just going to do this, and I say repeats. And we're going to write our yp now as ax e to the negative x. So there's your extra times x or times t, depending on the variables, right, from before. So now your yp prime is a product rule. Copy the first derivative of the second plus copy the second derivative of the first. And then we need the double prime as well. So that's going to be even more mess. So copy the first derivative of the second, just spits out -1, plus copy the second, which is e to the -x. Derivative of the first is -a. There we go. Plus the derivative of the second is just -a e to the -x. Good. And there you go. So now we are supposed to feed these guys into differential equation. Now, over here we see that we can simplify this. So if you can simplify anything, obviously, do it. You do not want to drag. These expressions could be, 2 lines of notebook long. You can have e to the x cosine 3x, right? And good luck with those derivatives on the second round. So simplify if you have a chance.
Professor?
Yes.
Shouldn't the middle term for y double prime p be positive? Because you have your negative a.
I am taking the derivative of -a x e to the x, copy the second term, derivative of the first is just -a.
Thank you. Thank you.
So that, right, and the formula will have a plus, right, from the coming into the product rule second term. So it is a -a e to the x. Good. No, that's very important to be clear. Calc 1 product rule. I mean, it's really a bad thing, right? When the grade for the differential equations suffers, right, because of the product rule or something like that. So please always make sure that. And guys, it's so easy for me to make a mistake over here. I mean, it's way too many minus signs, way too many rules done at once. So always double check everything I say and do here. All right, let's go. Plug in. So we have our y double prime. That's going to be a x e to the -x minus 2a e to the -x. And then we're going to have minus this one, the y prime. So minus ax e to the -x plus ae minus x. There we go. And then we have times -2 of the first one. And all of this needs to be equal to 4e to the -x. So here is your y double prime minus y prime minus 2 times y equals to this. So I hope you see what happened with those and where they were plugged in. They were plugged into the original differential equation. So now we just need to work out the algebra and figure out what a is. Ax e negative x minus 2ae negative x plus ax e negative x minus ae minus x minus 2axe minus x equals 4e negative x. Do we all see this? Apple plus apple is 2 apples. Take away 2 apples, they're all gone. What's left is negative 3a e to the negative x is equal to 4e negative x. from where negative 3a is 4, a equals negative 4/3. Like, like I wrestled with bears for like an hour. So we can finally write our solution. Y is equal to same complementary solution, c1e to the 2x plus c2e to the negative x. And here is a minus 4/3 x e to the negative x. We actually see the repetition and the form, right, where you have that multiplied. Remember, this part is the y prime part with a. Here it is. And it did have that x in there. So we just determined a, which was the unknown coefficient. We determined that coefficient as negative 4/3. That goes in here. The rest of the term has to stay as is. So that's your yp, and you know that your y is yc, which is this stuff, plus yp, which is this stuff, with the coefficient plugged in, which is all of these calculations you did before, you did down there, to come up with the a. And now I have my solution right here. Now someone can say y of 0 is 3 and y prime of 0 is 7. Go ahead, figure out these two in addition to all of the stuff, right, we did so far. That's another layer on the whole thing. So let's do one more example and then call it a day for the part 1 of our lecture. Part 2 next class, and then we will reset the stream and everything for the exam review, right? But let's do one more of these, see what else they have. And let's do one with initial values. It's gonna take us some time. So we did the polynomial problem, we did the trigonometric problem, we did the exponential repeated problem. So now let's just literally pick anything from the book. So someone give me a number between 31 and 41. 31 and 40. That's not a trick question. Just anyone pick a number.
33.
Thank you. Oh my God. 33. Oh-ho. Repetition on, oh, it's not a repetition on a trig. Okay. So this is going to be pretty much the same as our first example, except now we have to compute the, if this was a 3, it will be a repetition because 9, right? Square root of 9 is 3. Or if 9 was a 4, it will be repetition, whatever. Okay, y of 0 is 1 and y prime of 0 is 0. So we go and solve the homogeneous problem first. We know that r squared plus 9 equals 0. R equals plus minus 3i. And that gives us the complementary solution of c1 cosine 3x plus c2 sine 3x. That's that. And then for the second one, you either memorized the yp form of a sine, in this case 3x, plus b cosine 3x, or you went with that f is equal sine 2x and then differentiated f prime to get 2 cosine 2x and then f double prime to give you negative 4 sine 2x, and then you said, oh, okay, I have sine 2x's and they're changing. They go there, and then I have a cosine of 2x, and they should be changing if I had more derivatives, right? The next derivative would be a negative cosine underneath, so that would change its coefficient as well. So you either know how to do it step by step, like I always do, or you memorize the form when you see the solution. Oh, see, I made a mistake. It's not 3, it's 2. It's 2x. 2x. Okay, so yp prime is 2a cosine 2x minus 2b sine 2x. And the second one is negative 4a cosine 2x minus 4b cosine 2x. That's a basic chain rule from Calc 1. I put that all together. And then time to plug in these two into differential equation and figure out what a and b should be. So we're going to write our y prime. That's a negative 4a cosine 2x minus 4b cosine 2x plus 9 in parentheses a sine 2x plus b cosine 2. You can skip as many steps as you want. Like if you wanted to write this immediately as 9a and 9b, it will save you a step of writing. It is okay. So why do I have two cosines here? This is supposed to be a sine. Derivative of a cosine is a negative sine. So this has to be sine over here. Yep, good. So sine goes into cosine, cosine goes into negative sine. Cosine goes into negative sine goes into negative cosine. Good. That's my second mistake. Remember the first mistake? I put a 3 over here instead of a 2. I caught that. Because you always have to use the forcing term to come up with a particular solution. So that was my first mistake. The second mistake was not writing the derivative correctly, which would obviously make all of the coefficients to be wrong because these things would add up wrong. Now, I caught myself, obviously, for this one because I knew that I shouldn't have two, I should have two pairs, not 3 cosines and only 1 sine. Now, to the untrained eye, which is you guys, because you're just learning these things, obviously all of these mistakes would compound and not work out well at the end. So please focus, do it slowly, right? 9a minus 4a is 5a sine 2x. And then 9b minus 4b is positive 5b cosine 2x equals to sine 2x plus 0 cosine 2x if you want to. So now sine and sine have the same trig function, right? So it's 5a equals 1, a is 1/5, and then b has, if you really want it, here you go. So 5b is equal to 0, b is 0. So we don't write this, but you're comparing it to nothing. There you go. So we have that our yp is a is 1/5. So a is 1/5 sine 2x. Plus 0 for b, which would kill that cosine part. And the overall solution y is y complementary plus y particular, which in our case is C1 C1 cosine 3x plus C2 sine 3x plus 1/5 sine 2x. We are not done. This is general solution. Remember, we have the initial conditions, so we can compute C1 and C2. For that, we'll need y prime, which is negative 3c1 sine 3x plus 3c2 cosine 3x plus 2/5 cosine 2x when you take the derivative. So every time you're taking the derivative using the chain rule, right, you have to move the values in front. So this 3 pops out, and then later on in the sine 2x, 2 pops out as a multiplying coefficient. So now I have my y of 1 was, no, y of 0 was 1. So for this equation, y of 0 is 1. So that's 1 is equal to C1 survives, C2 dies because sine of 0 is 0, and this term dies as well. So we just got that C1 is 1. Awesome. Now, for the second condition, go away. For the second condition, we have 0 is equal to sine term dies, and then the cosine term lives. But it's equal to 0, so C2 is equal to 0, so C2 is gone. So what do I have for the solution now? It is going to be y, you can say y of x. And see, now it's kind of bad to use particular because particular was already used for this. We used particulars so far as a name for this solution when you compute everything at the end. So your C1 is 1, so that's just going to be cosine 3x. C2 is 0, so that term dies over there. And then you just have plus 1/5 sine 2x. And that is the solution, right, with C1 and C2 calculated. Ta-da! Welcome to Undetermined Coefficients. Now, next class, we are going to pick up Undetermined Coefficients and do another example where you can have, let's say, a combo on the other side. And I see them in the book. I mean, some of these have x squared cosine x, xe to the x, xe to the negative x, xe to the 3x times sine 2x. So you have all kinds of combinations that you can have them on the other side, and for those, we'll have to use the derivative to figure out which form is the form for undetermined coefficients. And at all times, you always have to keep one eye on your complementary part so that your particular part doesn't have repeats. So that's something that you really, really need to worry about. Obviously, more on all of this stuff in the next class. We're going to take a 5-minute break, and then when we come back, we have about we'll have about 35 to 37 minutes to come up with a plan for the exam, which you guys scheduled for this weekend. Not this weekend, sorry, for the next weekend. So yeah, here comes the epic music, and when we come back, we'll do more work.